So it's my first time to give talk in English. So, by the way, yeah.
Best of luck.
If you have any questions, yes, please. Anytime. So, today we use some facts we already learned before. So the first one is lemma 9.2, and maybe the condition R3 R is the condition root system. So this is for any R prime beta in pi and sigma in bar group, then beta alpha is equal to sigma beta sigma alpha. And number 2 is the table 1 in 9.4. That is for any R prime beta in E and R prime is not equal to beta, then alpha is beta, beta alpha is equal to 0, 1, 2, or 3. And the third fact is that lemma 10.1. So for any R prime beta in base and alpha is not equal to beta, then alpha beta is less than or equal to 0. And fact 4 is theorem 10.3. For B is that bar group X transitively on the basis, right? And for of C is that for any alpha in pi, there exists sigma in bar group such that sigma of alpha is contained in delta, and B is that bar group is generated by sigma alpha, that alpha is contained in delta. And the last fact is that plane in 10.4 is that pi is irreducible, depend on the if delta cannot be partitioned into proper subsets union. Such that they are solved like.
So today's chapter is 11, classification.
So first, I want to define the Cartan matrix. So this a base delta in pi, root system pi, and that dimension is L. So dimension of E of R is L. So definition. So we can fix ordering, right? Fix on ordering. Ordering alpha 1 to alpha L of simple roots, right? And then matrix generated by alpha I comma alpha j is called the Cartan matrix. Cartan matrix. Or pi. So we can expect that we fixed base, but the definition is the Cartan matrix of pi. So we can expect this Cartan matrix is independent of the base pi, the base delta, right? And the entries are called the Cartan integers. That is definition. So let me do the example. So we know the root system B2, right? So it looks like this. And I can give order, so ordering. So I said this is alpha 1 and I can denote it by alpha 2, right? So we can make a matrix. A matrix is always diagonal entries are 2, and we can get using very easy calculation. We can get this matrix. So remark. First is the Cartan matrix depends on the chosen order, right? So if we say this root is alpha 1 and this root is alpha 2, these two entries will change. Right? So it depends on the chosen order. But it's not a big problem because the Cartan matrix is independent of the choice of this delta. So that is because if delta prime is another base, then by factor 1, no, factor 4 of E. Yes, 4 of E. 4 of E. There this is sigma in Y group, such that sigma delta is delta prime. So alpha I comma alpha j is equal to sigma alpha I comma sigma alpha j. So they have the same Cartan integers, so they have same Cartan matrix. And third one is the Cartan matrix. The Cartan matrix is non-singular. This is because we can have a matrix equation. There is Cartan matrix, and times diagonal matrix inner product A1 over 2 to AL over 2. You can easily get this is just inner product. But because this is inner product, this is not non-zero determinant. determinant is non-zero. Because positive definite. And this is also non-degenerate. So this is also determinant is non-zero. That's why this is non-zero. I find define another root system with base delta prime alpha 1 prime to alpha L prime such that alpha I, alpha Z is equal to alpha I prime, alpha Z prime. So that means they have same Kappa matrix. And then the bijection. The prime says from alpha I to alpha I prime extend uniquely to a root system isomorphism. So this proposition says that therefore the Cartan matrix pi determines pi. Determines pi up to isomorphism.
Sorry, what was their argument for the non-singularity of the Cartan matrix?
Sorry.
Yeah, you gave an right. I mean, didn't you give an argument why it's non-zero, the determinant?
This two guys.
Yeah. Yes.
This I think this is positive inner product. So positive definite. So this is non-zero.
Yes.
So non-zero diagonal. Non-zero.
But the Cartan matrix is not diagonal. But you're saying it can be diagonalized.
This is Cartan matrix.
Yes.
And I think this matrix product, this matrix is equal to this matrix.
Yes.
And the determinant of this matrix is non-zero.
And the matrix on the right, you're saying it is certainly
non-degenerate. Yeah. So
just because I mean it is it's sort of it's the inner products of a basis
Right.
yeah.
Okay. Two guys have non-zero determinant. That's why. First, I want to construct isomorphism pi. So delta and delta prime is basis as of vector space, right? So we know that there exists uniquely vector space isomorphism pi e to e prime such that alpha I to alpha I prime. And then I want to have a commutative diagram. So for any I and j, sigma pi alpha j of pi alpha I log I j. By the definition of reflection, pi alpha j minus pi alpha j comma pi alpha I pi alpha I. But by the assumption, it's like the same with alpha j comma alpha I. And pi is just linear transformation, so we can make it by alpha j minus alpha j comma alpha I. So this is sigma alpha pi of sigma alpha j alpha I of alpha j. So this equation gives a commutative diagram E2 prime pi and E pi, and this is sigma alpha, and this is sigma alpha prime, and alpha is an element of delta, right? Because we alpha j's are bases, so we can extend the commutative diagram of E. And then I want to denote it by A. And then also we can get for any x in E, x alpha is equal to pi x pi alpha. This is because we can apply this equation about just any element of x, because this is commutative diagram. So we can put x in this position. So this is x and x. This is x alpha and x and alpha. So this equivalence is E. And we want to denote by E. And A and fact 4 of D. 4 of D is that diagram is generated by just a reflection of base delta. So we can extend this commutative diagram like this. E prime and E prime. Pi. This is just any element of pi group. Because sigma is where sigma is generated by sigma alpha something. So alpha T1 to alpha TK. It's like this. Then sigma prime is that sigma alpha T1 prime to sigma alpha TK prime. We can define it like this. And we can attach this diagram on the bottom, so we can make this commutative diagram. I want to.
You're saying you're extending because you went from sigma alphas to all possible sigmas. This is what you're saying.
Yes. Yeah, sigma is generated by just sigma alpha. But sigma alpha have commutative diagram. So we can attach this diagram and we can make it this commutative diagram. from C, you can get this equation pi sigma pi inverse is equal to sigma inverse, right? Just come to the diagram, and this is because sigma prime is sigma alpha t1 prime to sigma alpha tk prime, so sigma prime is in Bible. Right? I want to correct that. So it's time to ready to prove this vector space isomorphism is root system isomorphism. So we need to check two conditions, right? So the first condition is that pi, the root system pi is contained in root system pi prime. And we need to check also for any beta and gamma in pi, gamma beta is equal to pi gamma pi beta. Let's check these two conditions. First thing, let beta is in pi. Then by vector 4 of C, vector 4 of C, there exists sigma in bar group, and there exists alpha in base, such that sigma alpha is equal to beta. I need more space. And yes, so sigma beta is equal to no, pi beta is equal to pi sigma and pi inverse of pi alpha. Right? And by D, this is element of pi group, and alpha is just element of base. So pi alpha is element of delta prime, right? So this is included in so pi prime. That is why this is pi prime. That's it. And for plane 2, similarly, by vector 4 C, saying there is this sigma in bar group and there is this alpha in delta, such that sigma alpha is beta, then gamma beta is equal to sigma inverse gamma and sigma inverse beta. That is alpha. This is equals by using just vector 1, right? Vector 1. And using B, so we can take x by sigma inverse gamma. This is pi sigma inverse gamma and pi alpha by E. And this is same with, again, by vector 1. Using vector 1, we need to check these two guys element of pi. But this is included in delta prime, so this is included in pi prime, right? And these guys included in gamma is included in pi, and yes, this is also included in pi. And then by using plane 1, this is included in pi prime, right? By plane 1. So we can use fact 1. So we can attach sigma prime. Sigma prime is this one. Sigma prime by sigma inverse gamma is equal to sigma pi. But by using C, sigma prime pi is equal to pi sigma, so we can change it by sigma pi sigma, so pi sigma inverse, so this is equal to pi c, this is equal to pi gamma, and we can change it by pi sigma, so sigma alpha is beta, right? This is for proposition 11.1. I want to introduce sector graph and linking diagram. Delta is alpha 1 to alpha L. And this space. Then equal sector graph. This is L vertices corresponding to the element of base I, and there are edges I. The number of edges are alpha I, alpha j, alpha I. Between i's and j's vertices. I is not j. This is the definition of the sector graph of pi. Sector graph of pi. So remark. We can extract by the definition of cosector graph. Cosector graph is independent of delta because the definition is cosector graph of pi. The graph is independent of base. This is because if delta prime is another base, and you expect for of C, for of B, there is this sigma y group such that sigma delta is equal to delta prime. So it gives us alpha I, alpha j is equal to sigma alpha I, sigma alpha j. So they have the same Cartan matrix, Cartan integers, so they have same edges. So that is why they have same cosector graph. And remark number 2 is by just fact 2. Fact 2. These edges are 0, 1, 2, or 3. For example, let's look at dimension 2 root systems, A1 plus A1 E1, E2, and G2, G2. They have only two vertices, right? And because if you consider the root systems, the angle of between roots is 90 degrees, so there is no line. That is pi over 2. You can use table 1. Table 1 of in 9.4. And the angle of this is 2 pi over 3, so there's 1 line, and there this angle is 3 pi over 4, so there's 2 lines, because zeta is 5 pi over 6, there are 3 lines. So this is centered graph. But we need more information to recover the Catan integers, because we know the product of two Catan integers, but we don't know what is each one, the number each one. We need more information. To recover Catan integer. Because we cannot cover this. We cannot recover alpha I, alpha Z when this is 2 or 3. If the Catan integer is 0, these two guys always 0, so we know Catan integer. And if this product is 1, we know that these two values are negative 1. Between reading F3 is always negative. But if this product is 2, we don't know which one is negative 1, which one is negative 2, and three cases possible. So we need more information. So that is why we need thinking diagram. The thinking diagram. Fine. It's just cosector graph. Adding an arrow pointing to the shorter length loop. So, for example, let's look at B2 case. So, you know, B2 is like this. And this thinking diagram, this one is alpha 1, this one is alpha 2. And this vertex is corresponding alpha 1, and this vertex corresponding alpha 2. And there's 2 lines, and this is shorter one, so we can see arrow. This is thinking diagram B2. So let's look at F4. We will see about F4 next time maybe, but this is thinking diagram of F2. And if we have thinking diagram, we can recover pattern matrix. So if this is alpha 1, alpha 2, alpha 3, alpha 4, we can recover pattern matrix 2, 2, 2, 2, 2. And there is no line between alpha 1 to alpha 3, alpha 1 to 4. So 0, 0, 0, 0, similarly 0, 0. And yes, we can next one. Yes, because there's one line, so this value is 1, so this is -1, -1. Also, and this is 2 lines, but one of them is -1 and one of them is -2, but usually get because there is information about length of root covered.
For B2, you have maybe already, the carton matrix for B2 is
Matrix.
very easy, but
Yes. Oh, yeah, we did. We
yeah.
did wait. No. Oh, yes. This matrix.
It's sort of this block which is also in the middle there.
Oh.
I mean, of
Yeah.
course.
Because they're
Yeah.
same.
Yes, yes.
And then. I want to do calculation. Back to 3. Pi decompose always uniquely as the union of irreducible systems. In subspaces. System. It is to solve numbers. So, to prove this proposition, we need exercise 9.1. 9.1 is that if prime is subspace of E, and if sigma alpha of E prime is contained in E prime, then alpha is contained in E prime or of either. Or E prime and P alpha is a reflection hyperplane. Proof of exercise. So these two conditions cannot be happen together. This is because if you consider alpha comma alpha, so if the conditions hold together, alpha is in E prime and alpha is in P alpha. So alpha is 0, but it cannot be happening, right? Because alpha is non-zero. So we just need to show that if suppose E prime is not contained in P alpha, then alpha is contained in E prime. So there will be this data in E prime such that not contained in P alpha, so alpha beta is non-zero. Yes. And then sigma alpha beta is by the definition of reflection, beta minus beta alpha. But beta is yes, this thing is containing E prime, and beta is containing also E prime. So these guys need to element of E prime because this is non-zero. So alpha is and then we can prove proposition 11.3. Firstly, I want to check. Delta, I want to claim that delta cannot be partitioned into proper subset, union of proper subsets that so that depend on the sector graph of pi is connected. This is very obvious because if sector graph has two connected components, there is, for example, 3 points, there is, for example, 2 vertices, there is lines like this. So the vertices element of base, and then there's no line between these two components, that means they are orthogonal. These are the same. I agree. And then, yes, 1, 2, 3. Then assume that the sector graph consists of.
Do you mean it can be partitioned into?
Yeah, proper union.
Right.
And disjoint.
Right. If the graph is not connected, or
Sorry.
I mean, you're saying if and only if the Coxeter graph is connected.
Then cannot be partitioned.
Or cannot.
Yeah,
be
cannot,
divided.
yeah.
Cannot. Yes.
This is
Yeah.
T connected component. Say C1 to T. This one C1, this one C2, like this. And then let delta is delta 1 union to delta T be the partition. Corresponding to such that delta I is corresponding to delta Ci. By A, delta I are mutually orthogonal. orthogonal trace. Because delta i's are mutually orthogonal, so they're mutually orthogonal. And then, because delta is delta 1 union to delta t, and this is partition, so the intersection is empty and orthogonal. And define pi I is the subset of pi. Alpha is a G-linear combination of delta I. Then I want to claim that pi I ei is a root system. But it's very easy to check. R1, R2, R4 conditions are very easy to check because just pi I is contained in pi, and yes, the by the definition pi I is easy. And R3 is because R3 is that for any alpha and beta in pi I, then sigma alpha of beta should be contained in pi I by the definition of reflection beta minus beta alpha. But alpha and beta are elements of pi I, so they are the linear combination of delta I, and this is also integer because by R4, so this is just the linear combination. Okay. So I, EI is the root system. And then I want to claim that delta I is base. Check. Very clear. D1, D2. Very clear. D1 is delta I span EI. Yes, but by the definition of EI, it's very clear. And D2 is any element of pi I has linear combination of delta I, and all coefficients should be all non-negative or all non-positive, but pi I is containing in pi, so yes, it's very clear. So I think fact 5. Pi I is irreducible because yes, delta I cannot be partitioned, right? So pi I is irreducible. And then finally, we want to check that phi is equal to phi 1 union phi t. We check this, and we need to show that this one and this one are equal. But we need more information to prove this. The phi group. WI that's containing pi I is the subgroup of pi W generated by so by E, this is E, and this by E, sigma alpha x transpose trivially on I or any alpha is contained in delta G. G is not I. Right? Because they are orthogonal, so if alpha sigma alpha and an element of I, this is just x minus the x alpha, but this is 0. And we know that EI is WI invariant. So sigma alpha EI is contained in I for sigma. So alpha is contained in delta I. I. C EI is W invariant. Because an element of W of the form of sigma alpha like this. Alpha I and delta. So someone's containing in delta I and someone's containing in delta J. J is not equal to I, so this is trivial. And trivial means sigma alpha EI is contained. Trivial implies that this one. Alpha is in delta J, and alpha is in delta I. This is containment for support. Sigma EI for any sigma. So we can use exercise 9.1. Exercise 9.1. So I want to check. It's time to check this condition. This one is trivial by definition. By the definition of pi I, because pi I is just a subset of pi. Check. So alpha is in pi, and by D of sigma alpha I is in I, and by 9.1 sub 9.1. So there uniquely it is some J alpha. Alpha in EJ, but alpha is not in EI. Alpha is not in J. Then alpha is in EJ and alpha is in pi. So EJ is just span delta I, right? And the set pi. So this implies that because alpha is in pi, alpha is G linear combination of delta n in span delta I, right? So that's saying alpha is G linear combination of delta I. And then because alpha is contained in pi, and this is just the definition of pi I. So alpha is pi I, right? So this. And so we showed that it is sufficient to classify the irreducible root system case or the connected thinking diagram because by the proposition. So the next one is classification, but the proof is very long, so I think I need to do next time. Mm-hmm. Yes, and but I want to just write down the classification theorem.
Yes. This is a good ending.
Is pi is irreducible root system. Then pi has only A to G cases. Pi thinking diagram. Next time I will introduce about A to G cases. But however, we don't know if A to G cases exist. So in next section, so section 12, we will construct A to G cases, but we will just focus on A to D cases. So this is our next talk score. Yeah, that's it.
Yeah, as I mentioned perhaps before, so this is a classic theorem of 20th century mathematics, yeah. So I mean, we'll look into this proof then, and then after having done this, the next question is of course. I mean, did we already see that basically the Lie algebra or a simple Lie algebra is completely determined up to isomorphism by its root system? Did we see this? Maybe not yet. Yeah. So I mean, so the complete picture is basically to reduce the classification of semi-simple Lie algebras to the classification of root systems, then to classify the root systems, And then to show that for any such irreducible root system, there is actually a semi-simple Lie algebra with this root system. And for the so-called classical types, A, B, C, D, this is relatively, this is easy to show that there is such a semi-simple Lie algebra, and for the other types, one has to work harder. And we are not going to go into these details, these exceptional groups, E6, E7, E8, and G2 and F4. Yeah, so, then, what we'll do is then sort of classify the root system and root systems, and then say something. At least check in the classical cases that for each of those root systems we have a semi-simple Lie algebra, which gives rise to this root system, and then we also have to sort of say something about that a simple, semi-simple, simple Lie algebra is classified by its root system. Over algebraically close. Okay, but we'll do this in the next